right. So we've got a nice long weekend here. You get Monday off. I'll see you again on Tuesday. Hopefully you're done with 3.4. I'm not going to ask you for that today, but you better be done with 3.4. I will ask you about that on Tuesday. We're going to start covering 3.5 today. We're going to finish that up on Tuesday. Then we cover 3.6. We've got a couple days to review, and then the test is a week from Tuesday. Okay, that's our first exam. Now, a lot of the stuff that we're going to talk about today should sound pretty darn familiar. We're actually going to use a function that you learned about in 1010, did a ton with. I know Mrs. Karchner and I taught these in very similar fashions. So you should have this first part pretty well in hand. The function is not important. We're going to use a parabola over and over and over again for the first part of this discussion, and then we're going to change that. Because if you understand how a parabola works and how we transform a parabola, it shouldn't matter what function we're dealing with, whether it's the reciprocal square graph, a cube root graph, or whether it's a trig function, the ideas are exactly the same. So if you understand it on a simple function like the parabola, we ought to be able to kind of extend those ideas to more complicated functions. So again, the idea here is every function makes a shape, and when you know the shape and the pattern a particular function makes, we can take that graph and we can slide it up, down, right, left. We can stretch it, we can shrink it, not only vertically, which you're pretty familiar with, we can also do the same types of things horizontally. Okay, now, with the simple functions that we're dealing with right now, sometimes it's tough to tell the difference between a vertical stretch and a horizontal shrink, but hopefully we'll get there. There is definitely a difference in the way they're set up. In either case, whenever we transform these, well, that's weird, okay, this is called a transformation. And did I spell that right, Tylin? So you can't tell because my writing's so crappy, right? Okay, I think I did. All right, so the first part says, if the function is x squared, label 5 key points on the graph. So this is that idea that we went over the other day, and I'm just going to do this really quickly. Those 5 key points would be the same 5 key points that you did in 1010. Now, even though this graph looks kind of crappy, if I label this, even with my crappy handwriting and everything else, is that enough to convince somebody that I know what shape that is? Yes. It is. Okay, and again, we want to write down some of these ideas. Vertex is at 0, 0. Okay, and this pattern, and I believe Ms. Karchner taught this the same way, from the vertex, regardless of where we've moved the vertex, if you go to the right one, then you go up 1 squared. Up because it's always going to be positive, and squared because of the function itself. And then again from the vertex, if we go right 2, we go up 2 squared, and then we repeat that pattern on the left. So I go over 1, up 1 squared, over 2, up 2 squared, over 3, up 3 squared, and so forth. If I go back, I still go up 1 squared, go back 2 from the vertex, go up 2 squared, go back 3 from the vertex, up 3 squared, and so forth. We doing okay with that? That is the pattern that makes the parabola shape. Now, everybody listening? I know when I look through this stack of papers, this quiz, I'm going to see some XY tables. I know that because a lot of people rely on those. Okay? What you're doing by using XY tables to graph everything is you're crippling yourself. You really need to understand the pattern that makes the shape. Because if you're always making an XY table and figuring out what you're going to plug in, doing some math on it, and then figuring out the Y coordinate, you're doing 2 things. You're depriving yourself of learning why that pattern makes the shape, and you're also crippling yourself because you're saying, well, what if I move this to negative 22, 9? What if the vertex is there? Do you really want to be plugging in numbers that are around negative 22, 9? Thank you very much. I appreciate the backup there. Okay? So if you understand the shape, it doesn't matter where it was moved, how it was transformed. If you understand that basic shape, you don't have to rely on XY tables and the potential of making an error in your calculations and plotting the wrong point. You understand the shape and you know what you're looking for, and that's why we do this type of thing. Okay? So you're already familiar with this stuff right here. What happens if I take this shape, the x squared shape, and then after the fact, after I've squared to make the shape, I add 1. What happens? It goes up 1. Every single one of those points that I graphed before, all 5 of those key points right here, every single one of those is going to get moved up. Great, and this isn't my tablet, so I'm going to have to, let's see. I don't want that. I'm borrowing Miss Karchner's, and it is not set up the way I like it. There we go. They took it in to hopefully get it repaired. Irritating. Okay, we'll go with that. Okay, so, and now that I've zoomed in, so here's what the original one looks like. Looks like this. A shape we're familiar with. All I need to do is take all those points and move them up 1 here, up 1 here, up 1 here, and so forth. Now, if this used to be at 0, 0, now it's at 0, 1. If this one used to be at 2, 4, now that key point is at 2, 5. Now, I'm not going to label all 5 points on this. Is that okay? All right. So let's take a look at this one right here. Here I've plugged in x. I've squared it. Squaring makes the shape that we're familiar with. It makes that parabola that opens up. Then I subtract 3. What does that do to the graph? Okay, so it takes that same familiar shape and it's going to move all 5 of those key points straight down 3 units. So I go down 1, 2, 3, down 1, 2, 3, down 1, 2, 3, and like this. So that is the new graph. And again, I'd want to label a couple of those points. So this would be 0, -3. What would this one right here be? It would be 2, 2, 1, because it was 2, 4. You move straight down 3 units. Okay, now the good part about this is we've still got symmetry, so this point over here is going to be -2, 1. And again, there's no XY table, there's no plugging them in and then doing some arithmetic on it. We know the shape, we just know where we need to slide it in this particular case. So if we have a function, now notice this is different than what you saw in 1010. Whatever the function is, if the function makes the shape and then we add k to that after the fact, what does it do to the graph? Moves that same pattern up k units. If we subtract, it moves it down k units. And this is called a vertical shift. So that's called the vertical shift. Now this is really going to annoy me. I should have noticed that before. There we go. Got it on the toolbar. Excellent. Wonder, could I slide this? No. Okay, we'll go with that. We got less screen, but we'll deal with it for now. Okay, we slide down here, and we're going to go there. What does this change do? Okay, left 1. And what does this one do? Right 3. So now, is it okay if I don't take the time to actually graph those? I mean, you did those in 1010. We're good with that. So notice the difference here. We've got adding and subtracting on both of these transformations, but the difference is where we do that. Here we plug in an x, the function makes the shape, and then we add something or subtract something after the fact. That's going to change the y coordinate. That's going to be a vertical shift. Here, the very first thing we do when we plug in a number is we either add something or subtract something from the x, then the function squares or cubes or does the reciprocal or whatever it happens to be in order to make the shape. Okay? That's going to be a horizontal shift, and it does the opposite of what you'd think. So because we've got a plus here, it actually moves it which direction? Okay, that's going to be left, and this is going to be to the right. You with me? Okay. Now, I know the students in my class, I'd be disappointed if you didn't know what this was. Can somebody tell me why this moves it to the left 1 unit and this one moves it to the right 3 units? When it looks like you ought to be doing the opposite, right? Looks like this ought to be to the right and this ought to be to the left. Plus, minus, should match up. Yeah. Okay, it's when this equals 0. I'll buy that. Can somebody tell me another reason? Zach?
The plus is saying that it happened
Earlier. Okay, so if the regular parabola does this and makes the shape like that, by adding 1 to the x, it's going to speed it up. It's going to make it 1 unit sooner. So it's going to make it all of that 1 unit sooner. And this is going to delay it making the parabola by 3 units. So it's going to come down here, and it's not going to hit. Now, Justin said it's when it equals 0. Okay, look, it's not going to hit 0 until it gets to 3. Okay, so 3 on this one is going to act like a 0, when -1 on this one is going to act like a 0. Okay, not a huge deal, but it's important to think about why these transformations do what they do. Any questions there? Okay, let's take a look at the next one down at the bottom there. What does the negative in front of the x squared do? Okay, so it's going to be a vertical flip. It's going to be a vertical flip. It actually flips it across the x-axis. Now, for a lot of people, they think vertical, that's got to be y. Okay, but we're flipping it from top down to the bottom. Okay, so we're flipping it vertically. So this parabola is going to go like this. Same exact shape, same 5 key points, but instead of going to the right one from the vertex and going up 1 squared, we're going to go to the right one and down 1 squared, to the right 2 down 2 squared. So this is going to be 2 -4, 1 -1. That's still 0 0, -1 -1, and -2 -4. Any questions there? Okay. What type of transformations are these? Stretches or shrinks. What type? Horizontal or vertical? They're vertical. Okay. So these are vertical stretches or shrinks, and we can tell it's going to be stretched if A is greater than 1, and it's going to be shrunk if A is between 0 and 1. So essentially, if it's a number bigger than 1, it's going to be a stretch. If it's a number between 0 and a fraction or a decimal between 0 and 1, then it's going to be a vertical shrink. So normally the graph looks like this. So it goes here and here and here and here. So here's what the regular old parabola looks like. Okay, but on this one, it's been vertically stretched by a factor of 2. So we haven't split it left, right, up, or down or anything. If I go to the right one, I normally go up 1. But what does this 2 tell me I need to do? I need to go twice as far as I normally do, so I'm going to go up to 2. Normally I go over 2 and then up 2 squared, so that would be up 4. The 2 tells me I need to go twice as far, so that's going to put me at 8. And then the same thing happens on the other side. So I get this graph right here. So the dotted one is the original graph. The solid one is 2 times x squared. And this point right here, 2 comma 8. Instead of, what was it originally? Instead of 2 comma 4. Okay? Again, twice as tall. Vertically stretched. Took these points and made them taller. So it didn't do this. Everybody watch, please. It's hard to tell on this one. It did not do this. Okay? It didn't make it skinnier. Okay? Because that kind of implies that it's a horizontal change. See how my hands are moving like this? Horizontal. What it did is it took the graph and it made all the points taller. This is what it did. Now, is the effect, does it kind of look like it's skinnier? Yes, it does, and we'll talk about that in just a second. Okay? But what it did is it made the points taller. A better way to describe that is it made the points taller or it made the graph steeper. Made the points taller or it made the graph steeper. With me there? Okay, so let's take a look at this one. Again, the original one looks like this. And I'm going to zoom in big time on this one. What does the 1/4 do? Okay, fat and skinny, probably not a good way on this one, but that's okay. Okay, where does it move this point right here? Okay, this point right now is 2 comma 4. So I normally go over 2 and up 4. I'm going to go over 2 and up 1/4 as far as I normally do. So what's 1/4 of 4?
1.
1. So I'm going to be right here. Okay? That's too bad. Okay? I normally go over 1 and up 1 squared. I'm not going to go up 1. I'm going to only go up a fourth of that. Same thing over here, and same thing over here. So the graph looks something like this. Okay, now, does it look wider? Does it look fatter? Yes, it does. Was that the transformation, though? Did it do this? Everybody watch. Did it do this? No. What it did was it vertically shrunk them. It made the points shorter, or it made the graph less steep, more shallow, if you want to think of it that way. Any questions there? Sure? Okay, go ahead and flip the page over then. Okay, and this is where we want to look at each one of these and we want to think about how did these changes take place. You'll notice that I've got x squared and then I add 2. That's going to move it up 2, right? I've got x squared, that's that plain old parabola shape, that parent function, and then I subtract 1 from it, that's going to move it down 1. What's the 3 going to do? Okay, it's going to be a vertical stretch. Okay, what's the negative 2 going to do? It's actually going to do 2 things. The negative does one thing, the 2 does another. Okay, vertical flip from the negative and stretch. It's going to be taller than it used to be. Okay? Any questions there? Okay, now what I want you to notice on this, I know you can graph these, right? Everybody's good with graphing these? Okay, what I want you to notice is this is up and down, which is also a vertical change. Clearly, here we wrote vertical stretch and we wrote vertical flip and vertical stretch here also. So you'll notice that the first thing that happens when we plug a number in is we square to make the shape. Then if we either add or subtract or multiply it by a number, it's going to be a vertical change of some sort. So if we change it after we make the shape, then it changes it in a vertical direction. Okay? And it does exactly what you'd think. You would think that adding 2, if we're going to move it vertically, would be up 2, minus 1 would be down 1, and so forth. It does exactly what you think it would. Now, this next part, these are different. The first thing we do on this one is we add or subtract something. That changes the x, so that's going to change it horizontally. So if you change it before the function makes the shape, before we square in this particular case, it's going to change it horizontally, and it does the opposite of what you'd think. So adding moves the graph to the left, and subtracting moves the graph to the right. Because that's what this does, right? This is going to move it right 3, and this is going to move it left 4. Okay, now, am I going too fast? Are we okay? Is this all making sense? Nothing else? Think a little bit more in depth than what we did before. And again, this is where you explained why this does the opposite of what you'd think, what Justin said and what Zach said. Okay? So we come down here, and you did a whole bunch of this in 1010. Okay, so we're just going to practice this really quickly, and then we're going to take a look at a couple of other ones. Now you'll notice this is going to be different. It's a different function. It's a more complicated function. Okay, and we're going to be able to see some of these other transformations here. So on this problem right here, what does the 2 do? Okay, so that is I'm going to write vertical stretch. What does the 1 do? Left 1. And what does the 4 do? Down 4, right? So we're going to go ahead and we're going to graph that. So I need to move to the left. It normally looks like this. That's the regular one. I'm going to move it to the left and down. So left 1 and down 4. That's where the vertex is, and then I vertically stretch it. So I normally go over 1 and up 1. I'm going to go over 1 and up twice as far, so I'm going to go up 2. Now, keeping track of the fact that this is a symmetric function, I've also got this point over here. So if I know what this one is, I should know what that one is. And if I go over 2, I normally go up 4. I'm going to go up 8. So I'm going to go up to here. And then I've got this other point that's symmetric over there. So here's the graph I'm after. Now, does that look right? Does it look like it's been shifted to the left 1, down 4, and has it been vertically stretched? Are the points taller? Is the graph steeper than it used to be? Okay, that's what you want to think about. I know you already know how to do this, but those are the details you want to think about because in just a second we're going to be using a different function. Could we label these? -1, -4. If I went to the right 1, that puts me at 0. Up 2, that puts me at -2. If I went to the right 2, that's going to put me at 1. And if I went up 8 from -4, that puts me at 4. So everybody okay with that? Okay. And then, of course, we've got these symmetric points on the other side. This would be -2. This would be 4 here. All I need to do is just figure out what my coordinates are. This would be -3, and this would be -2. Are there any questions there? How could you check to make sure that we did this correctly? Yeah. If any of these points really are on the graph, they should work in the equation. So if you plug them into the equation, they better make the equation true. They will. We did this right. Let's take a look at the next one. This one's a little bit ugly because it's got the fractions in here. So what does the negative do? Okay, so this is a vertical flip. I really don't like these markers. See how that one does. Okay? What does this one do? Vertical shrink. So what we're going to do is we're going to make the graph not as tall. We're going to make it more shallow, not quite as steep. What does the 3 do? Left 3, because that's a horizontal change, and it does the opposite of what we'd think, and this is up 2. So left 3 and up 2. There's our vertex. And again, just for the heck of it, I'll graph just really quickly roughly what the original one looks like. Normally I go over 1 and down 1. I'm going to go over 1 and down a half. Normally I go over 2 and down 4. I'm going to go over 2 and down half as far, so only down 2. And then again, I've got these symmetric points over here. So my graph looks something like this. Arrows on the end. Let's be really convincing that we know what we're doing. This point right here was -3, 2. What's this one right here? Right there. Okay, so if I go to the right 1, that's going to put me at -2. And if I go down a half, 1 1/2 or 3/2 is how we normally write it. And what's this one right here? Okay, it is -1 and 0. Okay, now take a good look at those, because in just a second we're going to do some transformations that you probably have not seen before on a function that you probably haven't done transformations on before. Are there any questions? This all ringing a bell? This is easy. Thank you very much for making my weekend nice. We're good? Okay, so let's take a look at the next one. What's that? No, these are fun. These are fun. That's right. We're not done. Should you look at 3.5? Yes, you should. Okay. All right, so let's take a look at this one. The first thing we want to do is let's look at what the original one looks like. The original one would be 0, 0, 1, 1, and 4, 2, right? Here's the original. Okay, now think for just a second. There's a negative in there. Where is the negative? Am I multiplying by a negative before I take the square root to make the shape, or after I take the square root to make the shape? Before, right? If you change a function before it operates to make the shape, Is this going to be a horizontal change or a vertical change? Horizontal. So this is a horizontal. What did the negative do when we multiplied by it before? Outside. It was a vertical flip. Guess what this is? This is a horizontal flip. So here's what happens. I'm going to take this graph and I'm going to flip it horizontally. Now, horizontally means right to left. So we're going to flip it across the y-axis. So 0, 0 doesn't move anywhere because you're not really flipping that. And then I've got these points right here. Now, can you label those those 3 points? 0, 0. What's this one? Negative 1, 1. And this one? Negative 4, 2. Now, this is an even root, though, isn't it? Don't we have domain problems with even roots? How on earth can I plug in negatives? Okay, Parker? Because the first thing you do when you plug in a negative is multiply it by a negative. Negative times a negative is a positive, and you can take the square root of a positive. Let's double check ourselves. If you plug in a negative 4, negative times negative 4 is positive 4. Square root of positive 4 is 2. Is that point on the graph? Absolutely it is. And does it look like a horizontal flip of the original graph? It does. Remember, this is the original one. This is the transformation. You with me there? So that's a horizontal flip. So if y is equal to negative f of x, then the graph is horizontally, and I'm just going to write that a little better, horizontally flipped. In other words, it's flipped across the y-axis. Seems a little bit weird, okay? This is a horizontal change. The horizontal change because we changed the function before we took the square root to make the shape. Change the x before we took the square root to make the shape. Any questions there? Okay, now, that 2, we're multiplying by 2. Multiplying by 2. But we're multiplying before we take the square root to make the shape. So we're taking x. First thing we do is we multiply it by 2. Then we take the square root to make the shape. So we're doing this before the square root, right? My question for you is, and if you really get this stuff, you should know whether this is horizontal or vertical, number 1. And number 2, when we multiply by something, it usually stretches or shrinks. You should also know what it is. So if you think you have this all figured out, you should have 2 correct answers in your head. First part is this a horizontal or vertical change? And the second part is it a stretch or a shrink? Now don't say anything out loud because it would be really nice if everybody got this right on their own. We're changing the x before we take the square root. We're changing the function before it operates to make the shape. That tells you whether it's horizontal or vertical. Which is it? Horizontal. Okay? I won't ask for a show of hands, but hopefully you got that right. Now my question for you is this a stretch? Don't say anything. Stretch or shrink? Now we said horizontal changes are a little bit weird. What's weird about them? They do the opposite of what you would think they would do. So timesing by 2, you would think that that would horizontally stretch it, right? Well, let's just stick with the opposite for right now. You'd think this would horizontally stretch it. Guess what it does? It's a horizontal shrink. Because they do the opposite of what you think they do. Just like when you're adding 5 to the x, it actually moves it to the left 5 units. You with me there? So this is a horizontal shrink. So here's what I want you to do. Again, let's start with the original one. There's the original, and I'm going to change colors, and hopefully this actually shows up. Do the colors look any better today? I've put in a new projector. Hopefully it's looking a little better. Okay, now if this point is 4, 2, and I horizontally shrink it, I make it shorter. I should shrink it back toward 0, back toward the y-axis. What is let's see, if I multiply by 2, that would be like shrinking it by a factor of 2. So that would be like multiplying it by a half. Is that all right? So instead of 4, 2, shrink it halfway back, I should be at 2, 2. And 1, 1. Halfway back, that would put me at 1/2. And this is what the graph would look like. Looks like that. Now this point is 2, 2. And this one right here is 1/2, 1. Now what I want you to look at is this. Look at what coordinate changed. 4, 2, 2, 2, 1, 1, 1/2, 1. Which coordinate changed? The x did, because it's a change in the horizontal direction. Now, how can we check and make sure we got it right? And this is what Makia was talking about just a second ago. If you plug in a number, the first thing you do to it is you double its size. So if you plug in a 2, what do you get? You get a 4, then you take the square root, and what do you get out? You get out a 2. So did we do that right? We did do that right, and we're going to finish off by looking at this last one. And it says if you've got f of a times x, then the graph is, what do I put here? Horizontally stretched or shrunk. If a is greater than 1, then it's actually a shrink. If it's in between 0 and 1, then it's a stretch. So what's this going to be? It's going to be a stretch. So let's see if we can get this. Stretch. Now here's the original one. Looks like this. Still doing okay? If I take this point right here and horizontally stretch it, by how much would I have to stretch it? Kind of like a reciprocal relationship. I'd have to go 4 times as far. So this would be 4, 1. And this that was, what do we have, 4, 2, where would it end up? Change the x by a factor of 4, make it 4 times bigger than it used to be. It would be 16, 2. So way out there is a 16, 2. So 16, 2. So I get a graph that looks something like this. Horizontally stretched. Now, does that kind of look like a vertical shrink? It does. It's a little bit hard to tell the difference sometimes. You can actually manipulate them a little bit so they are. Now, if I plug in a 4, do I get a 1? 4. First thing I do is multiply it by a 4th. That's 1. Square root of 1 is 1. If I plug in a 16, do I get out a 2? Is that the right graph? Okay, think about that. Again, that's a horizontal change there. Have a great weekend. Please spend some time thinking about the front and back page of these notes here. We're going to deal with all those other functions that we dealt with before. We're going to do some transformations on those. So please think about it. Have a great weekend.